In today's video, we are going to prove a very interesting equality that involves trigonometric function, inverse trigonometric function, and also hyperbolic function. So the equality that we are going to prove is that the arc sine of the hyperbolic tangent of t is equal to 2 times the arc tangent of exponential of t minus pi over 2. So we will see that there are actually many methods to prove this equality. The first method, we are going to use the derivative of each function. We are going to show that f prime of t is equal to the g prime of t. And then we will integrate and show that the constant of integration is equal to 0. In the second method, what we are going to show is that the tangent of f of t is equal to the tangent of g of t. And based on the range of value that f of t can take and g of t can take, we are going to be able to conclude that f of t is equal to g of t. The third method, we are going to use the arcsine and arctine identities. So these identities might not be very well known, but you can actually find them on the Wikipedia page, and I provide the link of the page in the description of this video. For the fourth method, what we are going to do is we are going to use some complex numbers, and we will find a way to express arcsine and arctan using some inverse hyperbolic function and the complex numbers. So let's start with the first method. The first method will use the derivative of the arcsine and arctan function. So let's give a quick reminder of what these arcsine and arctan function are and how you can calculate their derivative. So by definition, we have arcsine, that is the inverse function of sine, and arctan, that is the inverse function of tan. This means that whatever the value of x between minus p over 2 and pi over 2, we have the arcsine of sine of x that is equal to x, and the arctan of tan of x that is also equal to x. So now the trick to find the derivative of arcsine and arctine is to use the derivative of a composition of function. So we know that when we have a composition of function u and v, the derivative of u round v is equal to u prime round v multiplied by v prime. And this is called the chain rule. We remember that a function that composes with its inverse is equal to identity. And we can differentiate the two sides of the equality. So we have u round u minus 1 prime that is equal to identity prime. Identity prime is equal to the number 1. And we have u round u minus 1 prime that is equal to u prime round u minus 1, everything multiplied by u minus 1 prime. And this is equal to 1. And so this means that the derivative of u minus 1 is equal to 1 over u prime round u minus 1. So if we apply this formula to arcsine and arctan, we have arcsine prime, which is equal to 1 over sin prime round arcsine. The derivative of sine is cosine, so this is equal to 1 over cosine of arcsine. And we know that arcsine can only take values between minus pi over 2 and pi over 2, so the cosine will always be positive. So we can use the formula cosine square plus sine square is equal to 1. So in other words, we have cosine, which is equal to the square root of 1 minus sine square. So arcsine prime is equal to 1 over the square root of 1 minus sine square round arcsine, which is equal to 1 over the square root of 1 minus identity square. So in other words, we have arcsine prime of x that is equal to 1 over the square root of 1 minus x squared for any value of x. We can use the same trick for arctan prime of x, that is equal to 1 over tan prime of arctan of x. We know that the tangent prime of x is equal to 1 plus tan square of x. So we can write that as 1 over 1 plus tan square of arctan of x, which is equal to 1 over 1 plus x squared. So now let's go back to the function f of t, and we can write that the derivative of f of t is the derivative of the composition of function arcsine of the hyperbolic tangent of t, and this is equal to the derivative of the function arcsine evaluated in the hyperbolic tangent of t multiplied by the derivative of the hyperbolic tangent of t. We have seen above what is the derivative of arcsine equal to, and we also know that the derivative of the hyperbolic tangent of t is equal to 1 minus the square of the hyperbolic tangent of t. So we can write that the derivative of f of t is equal to 1 divided by the square root of 1 minus the square of the hyperbolic tangent of t multiplied by 1 minus the square of the hyperbolic tangent of t. In other words, this is equal to the square root of 1 minus the square of the hyperbolic tangent of t. But we also know that the hyperbolic tangent of t is equal to the hyperbolic sine of t divided by the hyperbolic cosine of t. And we should also know the identity that the hyperbolic cosine square minus the hyperbolic sine square is equal to 1. So this means that we can rewrite the derivative of f of t as being equal to the square root of 1 minus the hyperbolic sine square divided by the hyperbolic cosine square. And we can rewrite this as being equal to the hyperbolic cosine square minus the hyperbolic sine square, all divided by the hyperbolic cosine square, which is equal to the square root of 1 over the hyperbolic cosine square, which is equal to 1 over the hyperbolic cosine of t. Now let's calculate the derivative of g. So we have the derivative of g, that is the derivative of 2 arctan of exponential of t minus p over 2. We have seen above that the derivative of arctan of x is equal to 1 divided by 1 plus x squared. So this means that the derivative of g de t is equal to 2 divided by 1 plus exponential of t square multiplied by exponential of t, and of course the minus p over 2 will disappear. If we multiply both sides of the fraction by exponential of minus of t, we have this quantity that is equal to 2 divided by exponential of minus t plus exponential of t. And this is exactly equal to the inverse of the hyperbolic cosine of t. This means that we have f prime of t that is equal to 1 over the hyperbolic cosine of t, which is equal to the derivative of g dt. So necessarily, by integrating both sides of the equation, we must have f of t that is equal to g dt plus a constant of integration a. In order to evaluate this constant of integration, we can simply evaluate this equation for t equals 0. So we have f of 0 that is equal to g of 0 plus a. This implies that the arc sine of the hyperbolic tangent of 0 is equal to 2 times the arctangent of exponential of 0 minus p over 2 plus a. We know that the hyperbolic tangent of 0 is equal to 0, and the arcsine of 0 is also equal to 0. We have exponential of 0 that is equal to 1, and the arctangent of 1 that is equal to pi divided by 4. So we have 0 equal 2 multiplied by pi over 4 minus pi over 2 plus a. So this implies that 0 is equal to pi over 2 minus pi over 2 plus a, which implies that a is equal to 0. So in conclusion, we just proved that f of t is equal to g dt for any value of t. Let's use the second method where we are going to show that the tangent of f of t is equal to the tangent of g dt. But before we are writing that, let's first evaluate to see if it makes sense to talk about the tangent of f of t and the tangent of g of t. So what we want to verify is that the value of f of t and the value of g of t belong to the domain of the function tangent. We remember that f of t is equal to the arcsine of the hyperbolic tangent of t. We know that the hyperbolic tangent of t can only take values between -1 and 1 and never actually reach the value -1 and 1. And we also know that if x belongs to the interval -1, 1 without ever reaching this value, then we know that the function arcsine of x belongs to the interval minus pi over 2, pi over 2. And this domain is actually an interval in which the function tangent is defined, so we are good. Now for g of t, we remember that g of t is equal to 2 times arctan of exponential of t minus pi over 2. Exponential of t is strictly greater than 0, which means that the arctangent of exponential of t is included between 0 and pi over 2, which means that 2 times this function belongs to the interval 0, pi, and this means that 2 arctan of exponential of t minus pi over 2 is included between minus pi over 2 and pi over 2, which again is a domain in which the function tangent is defined. So we are perfectly good here, and we can continue with the calculation of these two functions. So we can write that the tangent of f of t is equal to the sine of f of t divided by the cosine of f of t. We remember the identity that cosine square plus sine square is equal to 1. And since f of t is between minus pi over 2 and pi over 2, we know that the cosine is positive, so we can write the cosine as being equal to the square root of 1 minus sine square. So tan of f of t is equal to sine of f of t divided by the square root of 1 minus the sine square of f of t. And because f of t is the arcsine of the hyperbolic tangent of t, we can write that this is equal to the hyperbolic tangent of t divided by the square root of 1 minus the hyperbolic tangent of t square. We remember from above that 1 minus the square of the hyperbolic tangent of t is equal to 1 over the square of the hyperbolic cosine of t. So this is equal to the hyperbolic tangent of t multiplied by the hyperbolic cosine of t, which is equal to the hyperbolic sine of t. Now let's calculate the tangent of g of t. This is equal to the tangent of something minus pi over 2, which is equal to minus 1 over the tangent of this something, that is equal to minus 1 over the tangent of 2 arctan of exponential of t. A well-known formula for tangent is that the tangent of 2x is equal to 2 tangent of x divided by 1 minus the square of tangent x. So we know that the tangent of t is equal to minus 1 over 2 tangent of this arctan of exponential of t divided by 1 minus the tangent square of this thing. In other words, this is equal to minus 1 minus tangent square of arctangent of exponential of t divided by 2 tangent of arctan of exponential of t, which is also equal to minus 1 minus the square of exponential of t divided by 2 of exponential of t. And this is equal to minus exponential of minus t minus exponential of t divided by 2, or exponential of t minus exponential of minus t divided by 2, which is equal to the hyperbolic sine of t. So in conclusion, we have the tangent of f of t that is equal to the hyperbolic sine of t, which is equal to the tangent of g of t. Also, because we know that f of t and g of t belong to the domain minus pi over 2, pi over 2, and because the function tangent is injective over this domain, we can conclude that f of t is equal to g of t. Now let's check the third method that is going to consist in using the following identities. So some of these identities are maybe not very well known, but you can actually find them in the Wikipedia page in the link in the description. So the first identity is about expressing arcsine as a function of arctan, and you can express arcsine of x as being equal to 2 times x over 1 plus the square root of 1 minus x squared. The other identity is about expressing arcsine as another formulation of arcsine, and this is equal to the sine of x multiplied by p over 2 minus the arcsine of the square root of 1 minus x squared. So for those that don't know the function sine of x is simply saying that it is equal to plus 1 if x is positive and minus 1 if x is negative. The third identity is a bit more well known and is simply saying that the square of the hyperbolic cosine minus the square of the hyperbolic sine is equal to 1. And finally, the fourth identity is saying that when x is strictly greater than 0, we have the arctan of 1 over x that is equal to pi over 2 minus the arctan of x. So now we are going to consider two cases, a case where t is strictly greater than 0, and then later we'll see the case where t is negative. And we have f of t that is equal to the arcsine of the hyperbolic tangent of t, which is equal to pi over 2 minus the arcsine of the square root of 1 minus the square of the hyperbolic tangent of t. So in that case, the identity that we are using is that one, and the sine of the hyperbolic tangent of t is strictly positive, so that's why we can write this formula with pi over 2. We have seen previously that 1 minus the square of the hyperbolic tangent of t is equal to 1 over the hyperbolic cosine of t squared. So we can write that this is equal to pi over 2 minus arcsine of 1 over the hyperbolic cosine of t. And now we can use the first identity right here that is expressing the arcsine as a function of the arctan, and we have equal to pi over 2 minus 2 times the arctan of 1 divided by the hyperbolic cosine over 1 plus the square root of 1 minus 1 over the hyperbolic cosine square of t. We can simplify this formula as being equal to pi over 2 minus 2 arctan 1 over the hyperbolic cosine of t plus the square root of the hyperbolic cosine square minus 1. We know from the third identity that the hyperbolic cosine square minus the hyperbolic sine square is equal to 1. So we can write that this is equal to pi over 2 minus 2 arctan 1 over the hyperbolic cosine of t plus the hyperbolic sine of t. And we can write that because we know that since t is strictly positive, we also have the hyperbolic sine of t that is strictly positive, so we can put a plus here. Note also that the hyperbolic cosine plus the hyperbolic sine is equal exactly to exponential of t. So this is equal to pi over 2 minus 2 arctan of 1 over exponential of t. 1 over exponential of t is strictly greater than 0, and we know from the fourth identity here that if we take the arctan of 1 over x, when x is strictly positive, then it's equal to pi over 2 minus arctan of x. So we can write this as being equal to pi over 2 minus 2 times pi over 2 minus arctan of exponential of t. And we can simplify this as being equal to 2 times arctan of exponential of t minus pi over 2, which is exactly equal to g of t. Okay, now let's work on the case where t is strictly negative. So we have f of t that is still equal to the arcsine of the hyperbolic tangent of t. In that case, the hyperbolic tangent of t is strictly negative. So based on the second identity that we have here, we know that the sine of x will be equal to minus 1. So this will be equal to minus pi over 2 plus the arcsine of the square root of 1 minus the hyperbolic tangent square of t. This is equal to minus pi over 2 plus the arcsine of 1 over the hyperbolic cosine of t, which is equal to, as we have seen above, minus pi over 2 plus 2 times the arctan of 1 over the hyperbolic cosine of t plus the square root of hyperbolic cosine of t square minus 1, which is equal to minus pi over 2 plus 2 times the arctan of 1 over the hyperbolic cosine of t minus the hyperbolic sine of t. And the reason why we put a minus here is because we know that for t that is negative, we have the hyperbolic sine of t that is also negative, so we need to have a negative hyperbolic sine of t to have something positive here, because this quantity has to be positive. And we know that the hyperbolic cosine of t minus the hyperbolic sine of t is equal to the exponential of minus t. So at the end, this quantity is equal to minus pi over 2 plus 2 times the arctan of 1 over the exponential of minus t, which is equal to 2 times arctan of exponential of t minus pi over 2, which is again equal to g of t. And of course, we shouldn't forget the third case, in which case t is equal to 0, but we already know that f of 0 is equal to g of 0. So in conclusion, we have f of t that is equal to g of t, whatever the value of t is. Now, the trick of the fourth method is to be a tiny bit more artistic, maybe a bit less rigorous, and we are going to use the complex number. So the reason why it might not be as rigorous as the other method is because we are going to use the complex notation, maybe in some formulation that are not necessarily allowed. So the trick here is to notice that the sign of x can be defined as a sum of complex number, that is the exponential of I of x minus I minus x, everything divided by 2i, which a priori could be noted as the hyperbolic sign of ix divided by I. And based on that, we can show that the arcsine of x is equal to the inverse hyperbolic sign of I of x divided by I. And in the same way, we can show that the arctan of x could be expressed as the inverse hyperbolic tangent of I of x divided by I. And the two other formula that we are going to use for this method is the fact that the inverse of the hyperbolic sign of x can be expressed in the form of a logarithm, that is this one, and the inverse of the hyperbolic tangent of x can also be expressed as a logarithm right here. So, as I just said, the method that I'm going to present here, by using complex number, I may not completely be rigorous, and you are more than welcome to say in the comment what is the more correct way to do this, but based on the calculation, it looks like it's working quite well. So we start by expressing f of t as the, by definition, arcsine of the hyperbolic tangent of t. And based on the complex expression above, this is equal to the inverse of hyperbolic sign of I hyperbolic tangent of t divided by I. And based on the logarithm expression above, this is equal to the logarithm of I hyperbolic tangent of t plus the square root of 1 plus I hyperbolic tangent of t square divided by I. And we know that I square is equal to minus 1. So this is equal to the logarithm of I hyperbolic tangent of t plus the square root of 1 minus hyperbolic tangent of t square divided by I, which is equal to the logarithm of I hyperbolic tangent of t plus 1 over the hyperbolic cosine of t divided by I equal to the logarithm of I hyperbolic sine of t divided by the hyperbolic cosine of t plus 1 over the hyperbolic cosine of t, everything divided by I. And this is equal to the logarithm of I hyperbolic sine of t plus 1 minus the logarithm of the hyperbolic cosine of t, everything divided by I. Now, because it looks a bit complicated to simplify further this formulation, what we are going to do is that we are going to develop the formulation of g the t and try to see if we end up having an expression that is similar and hopefully identical to g of t. So we have g of t that is equal to 2 arctan of exponential of t minus pi over 2. Based on the complex expression, this is equal to 2 multiplied by the inverse of the hyperbolic tan of I exponential of t divided by I minus pi over 2. Based on the logarithm formulation, we have this that is equal to 2 divided by I of 1/2 of the logarithm of 1 plus I exponential of t divided by 1 minus I exponential of t minus pi over 2. This, in turn, is equal to the logarithm of 1 plus I exponential of t 1 minus I exponential of t minus I pi over 2, everything divided by I. And here the trick that we are going to use is that we know that I can be expressed with an exponential as being equal to exponential of I pi over 2. So we can write that I pi over 2 is equal to logarithm of I, if it is even allowed to express it this way. And we can write that pi over 2 is equal to logarithm of I divided by I. So this means that we can write g of t as being equal to the logarithm of 1 plus I exponential of t 1 minus I exponential of t minus logarithm of I everything divided by I. Now, the new trick that we are going to use is to multiply both the numerator and denominator by 1 plus I exponential of t. And this is in order to have a fraction in which only the numerator is a complex number. So we have this that is equal to logarithm of 1 plus I exponential of t, 1 plus I exponential of t, divided by 1 minus I exponential of t, 1 plus I exponential of t, minus the logarithm of I divided by I. And this is equal to the logarithm of 1 plus 2I exponential of t minus exponential of 2t divided by 1 plus the exponential of 2t minus ln of I divided by I, which is equal to the logarithm of exponential of t exponential of minus t plus 2I minus exponential of t divided by exponential of t multiplied by exponential of minus t plus exponential of t minus ln of I divided by I. So we just factorize by exponential of t here and there. And the next step will be to integrate the I from this logarithm inside this other logarithm. So this is equal to the logarithm of exponential of minus t minus exponential of t plus 2I divided by exponential of t plus exponential of minus t multiplied by I. This is the I from the logarithm of I that we have here. And everything divided by I. This is equal to the logarithm of I exponential of t minus exponential of minus t plus 2 divided by exponential of t plus exponential of minus t divided by I. And this is equal to the logarithm of I exponential of t minus exponential of minus t divided by 2 plus 1 divided by exponential of t plus exponential of minus t divided by 2 and divided by I, which is equal to the logarithm of I hyperbolic sine of t plus 1 divided by the hyperbolic cosine of t and everything divided by I. And this is exactly the same expression that we found for f of t. So we just proved that f of t is equal to g of t. So this is another way to prove the relationship f of t equal g of t by using the complex number. And as I said previously, I am not sure about how rigorous this fourth method is. So if you have any comment about how I can improve that proof using the complex number, please feel free to let me know in the comments below.